For every test you carry out on the Gleeble, you need to attach thermocouple to the sample. There are two ways to do that. You can either weld the thermocouple to the sample using a spot welder. This is a spot welding machine that I will be using to attach the thermocouple to the sample. You could also use the wraparound method. For some metals, it is very, very difficult to weld the thermocouple to the sample. So you have to use the wraparound method. And I think I'll show you that one in just a few seconds. But now, I'm going to show you how we weld the thermocouple to the sample. There are lots of samples. There are different types of samples that you can actually use for the flow stress test. You can use plain strain samples, which is like a cuboid, or you can use a cylindrical sample, as you can see here. But today, we will be working on the cylindrical sample, which is a uniaxial kind of test that we'll be carrying out on the Gleeble. So, I have a titanium alloy here that I want to weld a thermocouple to. So I need to place the sample right here and clamp it. Before doing this, I had already measured the length of the sample and divided it into two. Because when I weld the thermocouple, it must be at the center of the sample. So you have to divide the length into two and make sure that your thermocouple is welded at the center of the sample. That is at the mid-length of the sample. So we take the first thermocouple. And by the way, the thermocouple we are using today is called the chromel-alumel thermocouple, simply known as the K-type thermocouple. We have other types like the S-type, the R-type, the J-type, and many more. But today we are using the K-type thermocouple. So here, you need to peel out the polymeric material that has been used to insulate the thermocouple. Then you try to straighten it. And after that, you cut the tip of the thermocouple such that it's at an angle of 45 degrees. And after doing that, then you place this right here. And so you can tighten it here so that you can easily maneuver it here. There is a clip here. This clip must be on the thermocouple, the exposed thermocouple. You don't want that to be on the insulated area. Otherwise, there won't be any conduction of electricity. So now, the gap between the thermocouple and the sample should not be more than 2 mm. And there is a safety feature here that you need to override before you weld. Of course, you have to know the appropriate voltage for welding the thermocouple to the sample. For titanium, I used 34 volts, but it changes if you're welding to the thermocouple to steel or other type of sample. So that was a bad weld. I'm going to try again. You have to really be patient when you're doing this, otherwise you wouldn't get it right. If you don't get this right, you can't carry out your test. And this sometimes takes some time. So we've welded the first part of the thermocouple, and you need to weld the second part. I am not going to use this sample for the test we are carrying out today, because if I were to use it, I needed to insert a quartz tube from this end all the way to the welded region to help protect the thermocouple during the test. This would help you avoid thermocouple jump during the test. I'm going to use the wraparound method for the test, but it is important that I show you how this welding is done. So we have the second thermocouple, and we are going to weld it again. Like I said, you have to be patient when you're doing this, because if anything goes wrong here when you're carrying out the test, you might experience reverse polarity or thermocouple jump, which is something that you want to avoid, especially if you have limited samples. And the gap between the two thermocouples we are welding to the sample must not be too wide. It must be as close as possible for accurate measurement of temperature during testing. Like I said, this requires you to be patient. There you go. And yeah. And don't forget the gap between the sample and the thermocouple must not be more than 2 mm. You can't measure that, but you should be precise enough. So the second thermocouple has been welded. And now we are ready to set up the sample on the Gleeble machine. But don't forget that I mentioned that we're not going to be testing titanium today because we have run out of argon gas, so we're going to test aluminum, and we are going to do that under rough vacuum, because if you're testing titanium, you want to do that under argon environments so that you can prevent contamination of oxygen. So I'm going to show you the second method for attaching thermocouple to your sample. And here we have aluminum. And the aluminum is quite difficult to weld to the thermocouples. And for that reason, we use the wraparound method to do that. So I'm going to do that now. Again, you have to peel the insulation away so that you can have good contact. Should we have J-type thermocouple, we should be able to weld that easily to aluminum, but we don't have that. We only have the K-type thermocouple, which doesn't weld easily to aluminum. So we're going to use the wraparound method. So I'm going to wrap the ends of the thermocouple, and that's why it's called the wraparound method. If you check the Gleeble application notes, you would find this information there. It's much quicker than welding, but you have to do it correctly as well. So I already have one end wrapped quite well. Then I'll pick my aluminum sample and place it between it. Then I'll wrap again. And again, I had already measured the length of this sample. So the thermocouple must stay at the mid length. So, yeah. So you have your wraparound method and you have attached your thermocouple to aluminum. So we are set to load these on the Gleeble and carry out our thermomechanical testing for today. Before we leave, I would like to show you that my objective for today is to reduce the height of this sample to this. So I'm making a coin out of this aluminum. So this is 15 mm and this is about 5 mm thick. So the length is 15 mm, the length here is 5 mm. So we will be studying the flow stress as you deform from this height to this height. And the deformation would require high temperature as well as movement of the jaws to compress the sample into the desired height. So let's go to the Gleeble chamber where we would be setting up the sample.